In this code, various libraries and packages are imported and used throughout. For the collection and processing of data, the collections library is used. NumPy is used for scientific computation. Pandas is used for manipulating and analyzing data. Matplotlib is used to create visualizations. SciPyThsignal is used for signal processing. Statsmodels.nonparametric.kernel regression is used for non-parametric regression, and Yahoo Financials is used to extract financial information. Next, we define Yahoo Financials, which is populated with the stock or company name for which financial information is requested. The Yahoo Finance API will be requested using this variable. To get historical stock prices for the specified company, the code uses the Yahoo Financials getHistoricalPriceData method. HistPrices stores this data. Afterward, the code uses the default dict function to create a dictionary with a default value of none for all keys. Data for calculating prices will be stored in this dictionary. To create an array of dates from the historical stock prices data, the code uses the NumPy library. HistPrices entries are extracted by extracting their datetime keys. Using the variable dates, we can store an array of dates. In the next step, we will extract the closing prices from the HistPrices data and store them in a variable called prices. By looping through the data and utilizing the Yahoo Financials variable, we are able to find the close price for each financial instrument. The argral_extrema function from the scipy.signal library is used to find the local maxima and minima based on the closing prices once the dates and closing prices have been extracted. A maximum and minimum IDX are returned by this function. In the next step, the code generates a dictionary named price data to store each date's calculated data. Date, close, high, low, open, and volume are the keys that the dictionary is initialized with. By using a for loop, this code populates the dictionary by extracting the value from the dates and prices arrays, as well as from the extrema indices. Last but not least, the code performs kernel regression on the closing prices using the kernel reg function from statsmodels.nonparametric. In the matplotlib.pyplot library, the smooth curve of stock prices is plotted. This code retrieves historical stock prices of a specific company, calculates local maxima and minima, and plots a smoothed curve of the closing price using kernel regression. The code assigns values to three variables: start date, end date, and stock code, which represent the start and end dates of a time period, and the stock code of a company, in this case Facebook. Variables can be changed to fit any desired time period and stock code. Rather than performing any operations, this code simply initializes the variables that will be used for further analysis or processing. Three parameters are passed to this Python code: start date, end date, and stock code. In the stock data variable, historical price data is obtained from the Yahoo Financials library between given start and end dates for the given stock code. A daily data retrieval is performed. Using the stock data dictionary, only the prices for the given stock code are extracted for the price data variable. In order to create the final data frame, the columns variable must be created next. A new columns variable is created to rename the columns to something more user-friendly. In the following line, a new data frame called df is created with price data as the data and columns as the column names. In this case, the data frame columns are arranged in the desired order. Next, the df data frame's column names are updated with the new columns names using the rename function. In conclusion, the code returns three values: the df data frame, the close column, and the date column. It takes in start date, end date, and stock code inputs, retrieves historical price data between those dates, and creates a data frame with the desired columns. In this code, we call preprocessed data with parameters start date, end date, and stock code, assigning the return values to df, prices, and dates. Based on the variable names, it appears the preprocessed data function takes some stock data over a certain time period and preprocesses it in some way. df, prices, and dates are then available for use in the rest of the code, likely for additional stock data analysis. The code first imports the NumPy library, which provides support for large, multidimensional arrays and matrices, as well as a large collection of high-level mathematical functions. Using NumPy, the next line sets the index to a NumPy array of values ranging from 1 to the length of the prices variable. This creates an evenly spaced index for the prices variable. A NumPy array with values ranging from 1 to the length of the dates variable is created next for the index of the dates variable, creating an evenly spaced index for the dates variable again. It is used in Nadaraya-Watson kernel regression, a method of estimating the conditional expectations of random variables, which is non-parametric. Price and date variables are represented in the regression model as dependent and independent variables. Index values that are evenly spaced enable calculations and visualizations of the data to be performed more easily. The following Python code accesses the head function on the dates object. A dataset's first few rows are commonly displayed using this function in libraries like pandas. Using the head function, the first few rows will be shown, typically 5 rows by default, as an example. By doing this, you can quickly understand the structure and contents of a dataset without having to view the entire dataset. An array called price's first 5 rows will be displayed in this code using the head function. Data manipulation and analysis are commonly performed using pandas, a popular Python library. A quick preview of the data with this code can help you gain a better understanding of its structure and values. Python code for analyzing technical analysis empirically. This code identifies local minima and maxima in a time series using a smoothing technique. In this code, the function findMaxMin takes in the price data and uses the kernel reg function in stats models to create an object model. In order to find the optimal bandwidth, this object uses cross-validation to fit a smoothing curve to the prices data. Resulting from this method is smooth prices, a series of smoothed price data similar to the original data. To identify the local maxima and minima in the smooth price series, the code uses the argRelExtrema function in scipy.signal. As a NumPy array, this function returns the indices of the local maxima or minima based on the smooth price values and the comparator function greater or less. After that, a for loop filters the local maxima and minima based on their indices. It ensures that the identified points are true local extrema by only considering points within the smoothed series window T1 and T+1. In the smooth price series, indices are chosen that are 2 positions prior to and 2 positions after the identified index. This is done using the iloc function from the pandas library. As a final step, the code creates 2 pandas series objects, price max and price min, which contain the maximum and minimum prices at the identified indices. We then concatenate, sort, and deduplicate the 2 series to remove any points with both maximum and minimum values. As a result, the series max-min contains the final list of local minima and maxima in the original price data. This Python code uses a smoothing technique and additional filters to identify and return the local minima and maxima in a given time series. For further analysis, it also creates a smoothed price series. There are 4 variables in this code: smooth prices max indices, smooth prices min indices, price max indices, and price min indices, which are all evaluated with the argument prices. As an argument, findMaxMin likely takes a list of prices and returns the following values. 1. Smooth prices, a list of smooth prices, likely based on moving averages or other smoothing methods. Smooth prices max indices, indexes where smoothed prices reach a local maximum. 3. Smooth prices min indices, indexes in which smooth prices reach a local minimum. The price max indices are the indices in which the original price reaches a local maximum. A list of indices where the original prices have reached a local minimum. The input list's maximum and minimum prices are represented by the tuple max-min. Following this, the code calculates or analyzes the values. Understanding this code requires knowledge of the implementation of getMaxMin and its context, as well as the context in which it is used. With the head function, this code prints the length of the max-min data frame and then displays the first 5 rows of the data frame. By default, the head function displays the 5th row of the data frame to provide a quick overview. It plots prices over time, along with smoothed versions. In the first line, fig and ax are assigned a figure with the specified size and resolution. On the figure, the following 2 lines plot prices and smooth prices. As shown in the next line, the tick marks on the x-axis will appear every 30 days. The next 4 lines assign maximum and minimum prices for smoothed and regular prices to variables. By using the dates and values from the previously extracted variables, These 4 lines plot the maximum and minimum values on the graph. The scatter plots are colored and labeled differently. It adds a legend to the graph when ax.legend equals upper left is set. As the graph progresses, grid lines will be added. With this code, we produce a graph that shows a relationship between prices and time, as well as highlighting price maxima and minima points. In this code, stock prices are plotted over time, as well as the smoothed version and notable maxima and minima points. Input parameters such as dates, prices, and indices are used to create a plot. In the first step, it checks if an axis argument was provided. In the absence of this, it creates a figure and axis with specific dimensions and DPI depending on the file format. Next, the NumPy linspace function is used to evenly space the ticks on the x-axis with the original prices, smoothed prices, and smooth prices. Next, it calculates and plots the smooth prices maxima and minima along with the original prices. These points are calculated based on the parameters indices. Lastly, grid lines are added and the plot is labeled with a legend. In summary, this code creates a visual representation of stock prices over time by highlighting key points and smoothing the data. The following code is a function called plot window that accepts a number of parameters: dates, prices, smooth prices max indices, smooth prices min indices, price max indices, and price min indices. In response, the function plots the given data from start to finish along the x-axis. This function takes 2 arguments, dates and prices. Dates is an array of dates to correspond to prices. Smooth prices is a list or array of smooth prices calculated from the original prices. In the 4th and 5th arguments, smooth prices max indices and smooth prices min indices, you specify the indices of the maximum and minimum smooth prices. Prices max indices and prices min indices work similarly, but for the original prices. There are 3 optional arguments: start, end, and ax. The start and end points define the range of data to plot, while ax specifies where the plot will be generated in a matplotlib axes object. In the first step, the function plots the original prices, data as a line plot with the dates on the x-axis and the prices on the y-axis. On top of the original prices, the smoothed prices are plotted as lines. As well as the smoothed prices, the original prices are also marked with X symbols to depict their maximum and minimum values. Furthermore, if the price max indices and price min indices arguments are provided, the function will also plot a dashed vertical line at each of the indices, highlighting the maximum and minimum points of the original prices. Finally, the function returns a matplotlib axes object containing the plot. Stock market data is analyzed using this code. Using max-min as a data frame, it creates a dictionary patterns to store the different patterns found. A sliding window of 5 days is evaluated during each iteration of the data frame. More than 36 days of the window will be skipped. Next, the code assigns variables to the first 5 data points in the window and calculates the mean of certain groups. In this case, it checks for different patterns using if-elif statements, such as head and shoulders. It then adds the start and end dates of the pattern to the appropriate dictionary entry. The dictionary is returned with all the patterns identified and their corresponding dates once all windows have been checked. As written, this code does not work. Patterns equals find patterns max min indicates a function called find patterns that takes an input called max min. It is unclear what the find patterns function does or what it returns after this line. Due to this, it is impossible to determine how the code works without more information. As a result of this code, a dictionary named shorthand full-name dict is created with a series of key-value pairs. Chart pattern keys, such as HS for head and shoulders, are abbreviations. Values are full names for chart patterns. To quickly refer to these patterns, use this dictionary. As an example, shorthand full-name dict, HS, returns head and shoulders. With the help of this code, you can visualize. It utilizes input variables such as dates, prices, patterns, and dictionaries to identify different price patterns for specific stocks. A loop first loops through each pattern in the pattern's variable and prints out its shorthand name and number of observations. Using matplotlib, it creates a figure with multiple subplots by calculating the number of rows needed. A plot window function plots the price data and markers for each identified pattern using the plot window function. The user is then presented with the final plot. With this code, you are able to analyze and make investment decisions more easily by identifying and visualizing patterns in the stock price data. In this code, first we define a function named visualizePatterns, which accepts several parameters: dates, prices, smooth prices max indices, smooth prices min indices, price max indices, price min indices, patterns, and shorthand full name dict. In the function, various plotting functions from matplotlib are used to display patterns and trends. First, it creates an axis and figure for the plot. Using the axes and dates as axes, it plots input prices and smooth prices. In the following step, the smooth prices max indices and smooth prices min indices parameters are used to plot the maximum and minimum points for the smooth prices. A plot is then generated using the price max indices and price min indices parameters to show the maximum and minimum price points. A legend is then added to the plot using the patterns and shorthand full name dict variables. The code provides a way to visualize patterns and trends in financial data, making it easier to analyze and interpret. A simple code is described here that calculates and prints the average of a list of numbers. This code defines a function called calculateAverage that takes in a list. The function then uses the sum function to calculate the sum of all the numbers. After that, it uses the len function to calculate the list's length. Calculate the average by dividing the sum by the length. Lastly, we print out the result. If the input list is 4, 6, 8, the output will be 6.